Today we're going to learn about how to show students how to add with variables and equations. And we're going to begin with either concrete items like candy bars and money, or even semi-concrete, moving to paper candy bars. That's going to be our major theme here, though, using candy and money and figuring out how much a candy bar costs or part of a candy bar costs. Okay. So we want to kind of introduce the students with the situation. So we'd have each student create a sheet like this with two large rectangles on it, and then a little answer area. We'll call this down here. Okay, and so we're always trying to get students to understand the situation, what's going on, because too often we have students try and solve things. We try and show them abstract methods, how to solve things, without really understanding what's going on in the situation. That happens a lot with word problems, where we'll put a word problem on the board and immediately we'll write an equation to it and start answering and start solving the equation. And the students really don't understand what is going on in the problem itself. Okay, and that is a major deterrent for them to really understand the mathematics. So the first thing is, here we're going to use concrete items, and we're going to understand the situation. So like I say, a person goes into a store with 46 cents. So I want the student to represent 46 cents in the left box. This is what they're walking into the store with. Okay, and they come out of the store with two candy bars. They use this money, and they purchase two candy bars. So they come out of the store with what you see represented here: no money and two candy bars. Now I have the students, without speaking, without writing, use the manipulatives and show me the cost of each candy bar. Each candy bar costs the same amount, by the way. One isn't more expensive than the other, and we have to let the students know that. Okay, so typically what the students do is, some of them you can kind of mentally see what this is going to be, but I want them to move these manipulatives around and line them up to show me the cost of each candy bar, and they can do it in a lot of different ways. Okay. All right, I might get something like that. All right, I'll ask the students, okay, so why did you break this into two equal groups when you did this? And they'll say, well, because I had two candy bars. All right, and I can say, okay, let's for purposes, you solve this, but when you find an answer, how about putting it down here? So I know I can ignore all this, whatever's up there, and I can just focus down here. Okay? We might do another one, such as a student or person has 4 candy bars, so they begin with 4. And have them put in the left box. And they're all identical. They sell them to a friend for 48 cents. So in the right box, I want them to put 48 cents. Now, they're going to sell all these for 48 cents. So what can they tell me about the value, what this box is worth, the items in this box, compared to the items or the money in this box? What can they tell me about that? And the idea is that they're equal, they're the same. Okay, and so I'm going to use my math symbol to represent that in between. All right, so I'm asking them to show me the cost of each of the candy bars. And again, typically they break this up into 4 groups. Okay, I gotta exchange my nickel, which is okay. Okay, I'm gonna bring this down here. Okay. So again, I want to talk about it, and I want to really look at their physical interactions. I'm gonna say, okay, so I'm seeing that a candy bar is worth 12 cents, and I'm ignoring all this up here. Well, last time, in our last problem, you broke this into 2 equal groups. This time you broke it into 4. Why did you break it into 4? And they're pointing to the candy bar. They're saying, this is what tells me how many groups to break it into. Last time I only had 2 candy bars, this time I have 4. Okay, so that's very important. We're focusing over here to figure out how to break this amount of money equally. Okay, after they've done maybe 2 or 3 of these, I can start to translate these physical, concrete models into the abstract. I'd say, okay, so in the beginning we had 4 candy bars, and we didn't know the cost of any of them. What do we do when we don't understand, we don't know what the cost is of something? How do we write that mathematically? And we use a variable. Okay, so there's really 2 ways I could represent the idea that we have 4 things we don't know what they cost. One is I could, and I'm going to use the letter C. There's 4 candy bars, where C is the cost of a candy bar, and it's the same as, it's equal to 48 cents. Okay, now I could look at this too, and I could say, okay, is there another way I can write the idea of having 4 items that we don't know what the cost is? And they might have some trouble with this. I'd say, okay, well, if I know the cost of 1 item, can I multiply that by 4? Okay, and of course the answer is yes. So could I write this like this? 4 times the cost of 1 candy bar is the same as 48 cents. Is that true? Okay, so we have 2 ways to write this. All right, and I'm going to focus on this way right here of writing it. And I'm going to give the students, I would probably give them 1 or 2 problems to really make it useful to do this. Like, for example, if I said, I have 16 candy bars that cost, a certain amount of money. Okay, go ahead and solve that. How would I write it? Well, writing C plus C plus C 16 times versus writing 16 times C, I give them a reason, a good reason, to write it in this format. Okay, because it's just easier. Okay, so I could do 1 or 2 problems like that. Okay, so right now we've just modeled the concrete with the abstract. Okay, so far so good. But what our goal is always to figure things out in the abstract very efficiently. Okay, so looking at this here, I could say, all right, when you had all this together and all this together, you broke this into 4 equal groups, and why? And again, it's because I had 4 candy bars. Okay, if I were looking at this equation right here, rather than having the actual candy and the money there, what would indicate to me that I'd need to break it into 4 equal groups? And of course, it's the idea of that, the 4C right there. Okay, and when I break this into 4 equal groups, what am I doing in terms of mathematics? Am I adding? Am I multiplying? What is it I'm doing? And the idea is I'm dividing it 48 into 4 equal groups, division. Okay, so if I want to represent that here, how would I write that? Well, the students might say divide by 4, I'm sorry. And of course I'm going to divide that by 4, and that's okay. That's true. That's mathematically correct. All right. Or I might, and I probably would stick with their way of doing it for the first few problems, because if that makes sense to them, that's what I'm going to do. And it's accurate, so long as it's accurate, and it is. Maybe after we've done a few of these problems, I would also introduce another way to do this. Okay, and that is thinking of this as a fraction, 48 over 4. Is that the same thing as this right here? And yes, it is. This is another way to write division, another way to represent division. And 48 over 4 is, in fact, 12. So, will that give me 1 candy bar equals 12 cents? And yes, it does. Okay, so what I'm doing here is I'm beginning in a concrete, I'm understanding the concrete setting, understanding the situation there. I am, the movements I use here, I'm mimicking down here. I'm representing it and mimicking them down here. So if they take 4 and divide it 4 ways and 48 and divide it 4 ways here, I'm going to do it here. And this is where the rules are coming from. Okay, now I can start to, again, play devil's advocate. I could say, well, how come, okay, so I divide that by 4 like I did here, so 4 candy bars equal 12 cents. And the idea is, well, no, if you divide that 4 into 4 equal groups, you have to divide this into 4 equal groups. And there's the idea of what you do to one side, you do to the other, or the sides have to be in balance and so on. But they can tell you because they understand the situation. You don't have to give them all these rules. All you're doing is you're giving them a situation, you're helping them to model it mathematically, and then you're imitating what they did here. They're writing the rules here. You're imitating that down here through things like this or writing like that. Okay? Okay, so those are the first types of problems that we do to try and get students to understand what's going on. And notice at the very end, though, I'm ignoring all this up here and I'm just focusing on this right here in the answer area. Okay, well, we could try a few more of these types of problems, beginning to concrete, have them represented abstractly in the writing. And at some point, I'm going to give them a problem where I'm going to say, hey, do you think you could solve it without using the manipulatives? How would you solve something like that? And pretty much the students are going to use this experience, which is very deep and very meaningful, to help them with this. Many of them are going to look at this and say, okay, that's like having 6 candy bars in the left box and 42 cents in the right box. And I'd break this into 6 parts. So I'm going to break this into 6 parts. So, and again, it's what's often in math terms we'd say, what's the coefficient on the variable? That's what we divide both sides by. But in math terms, that isn't very meaningful. Okay, it's identified mathematically and talked about in mathematical terms, but the rule is not because a mathematician made it up. The rule is because that's what's happening in the real world, and we want this to represent what's going on in the real world. So now the students can start figuring out how to solve an equation. A variable multiplied by a coefficient equals a number, and they can solve it abstractly. And so step 1 is done. We could give the students, again, something that maybe makes it even more useful. Like, for example, what if I had 325 candy bars that were worth, like maybe $10.50 some cents or something like that. I wouldn't want to put all those candy bars down here and try and figure it out. I would want to do it abstractly. Okay, so here you have a variable on one side and a number on the other. Now we're going to look at problems in the concrete again, and we're going to put variables on both sides of the equation. So let's say in box 1, you have the students put in 3 candy bars, and you say one student has 3 candy bars and another student has 2 candy bars, the same type. All the candy bars are exactly the same, they cost the same, and 15 cents. All right. So one student has 3 candy bars, the other one has 2 candy bars, and 15 cents. And you say the value of that student 1 of their items is the same as the value of the items that student 2 has. So what's the cost of a candy bar? All right. So in this case, the students are going to kind of look at this and kind of analyze. And again, you say no talking, no writing. You have to do it all right here. It's important that they do it here, because these physical movements lead us to the rules, just like last time here. If they just see it intuitively, or they write it, they figure it out any other way, it's going to be very difficult to say, oh, I just saw it and write the answer here. Okay, we need those physical movements here that guide the abstract movements here. Okay, so a lot of students are going, and I'm walk around and watch them, and they might do something like this. Just kind of line them up, and then of course put this in the answer thing here. Some might do 1 or 2 like that, just getting the students to understand again the situation. Let's say this was the third one here. Let's just say this is the third time, and now we're moving to an abstract situation. I'm sorry, understand the concrete situation here, and we're going to move to the abstract. So we'd say, okay, what did we begin with? And the idea was, okay, we began with 3 candy bars and 2 candy bars and 15 cents, and we said that they were equal, they were the same value. And what did I do? Okay, well, I kind of lined them up, and then I ignored these 2 here, this part of it, because I brought this down. Okay, So looking at it here, when you line these two up and ignore them, where are those two here? Where could you find a two equivalent? Well, you could say it's these two here, and we're taking 2 out of the 3 here. We're taking 2 out of the 3 here. That sounds like we're subtracting, taking away 2 candy bars from the 3. And here, it's like we're taking this away, or ignoring it, if you want to think of it that way. And when we do that, when we take this off and take this off, or put them up here and ignore them, in effect we're taking them out and we're left with 1 candy bar is equal to 15 cents. Okay, so that's kind of what we're doing. We could do it this way as well. We could put everything in the answer area and begin with 3c equals that, and then say, okay, well, I can take away 2 of these and 2 of these, leaving me with this, take away 2 of those and 2 of those, leaving me with this right here, and that gives me the answer. So what goes on up here, that's the rule down here. Okay, rather than us saying, oh, you got to combine all the candy into one side, or whatever this is, you do the opposite. Okay, the students are going to tell us what to do. Okay, and so and the rules have meaning to them. All right, so we have 1 kind of candy bar is equal to 15 cents. We could try another one, and again, if we want to use this model here, we put everything down here, 4 candy bars and 3 candy bars. And we could have 5 cents here. And we could just put 10 cents over here. Okay, again, the value here is the same as the value here. This candy bar costs the same as all the other candy bars. What's the cost of a candy bar? Okay, and have the students physically move these actions and say, okay, well, this and this are the same, so I can take those away. And this is the same, I can take those away. This and this is the same, take those away. And okay, I've got 5 here and 10 here. Maybe what I'll do is I'll just exchange 1 dime for 10 pennies. Okay, and now I take 5 of these and 5 of these because they're the same. 1's equal to 5 cents. Okay, so let's go back and let's write it mathematically. We began with 4 candy bars and 5 cents on the left, being the same value as 3 candy bars and 10 cents on the right. And what did you do? Now, it's not wrong for students to say, well, the first thing I did was I took 1 candy bar from here and 1 candy bar from here. And I can do that here, and that's mathematically correct. I could say, okay, so you took away 1 candy bar, and you took away 1 candy bar, and you were left with 3 candy bars and 5 cents, and 2 candy bars and 10 cents. Okay, what did you do next? Well, I took 1 candy bar and took 1 candy bar. Okay, I can do that here. 2 candy bars and 5 cents equals a candy bar and 10 cents. Okay, and then I did it again. That's okay. All right. You could, as a class, once you did this, you could say, well, was there a faster way I could have gotten rid of those candy bars? Because you've seen it be a little bit faster than doing 1 at a time. And then they start to say, oh yeah, I guess I could have taken all 3 at the same time. Okay. And I could ask them, why 3? Why not 2? Why not 4? And they could start to give me good reasons for doing that. Okay, rather than mathematical abstract language, they can give me good, real reasons for doing that. Okay, so they could look at this, they could say, okay, well, there were more here and less here, so I knew I was going to have to take away and get all these gone here, so I needed to get the candy bar by itself. We call that in math, isolate the variable. Okay, and we teach the students that. Well, here the students are telling us that because they understand the situation. That's the power of this way of learning. Okay, the students tell us that. Where if I try and convince them of something that's wrong, like I'd say, okay, I want to take 7 candy bars from both sides. They'll say, well, you don't have that. I say, well, I got 4 and 3 is 7. I say, no, that doesn't make any sense. You see, they can actually, because they understand it, they can be very tenacious, they can be very stubborn, because they understand the situation so well. Whereas, in a traditional math classroom, if I said, oh, let's take 7, I see 4 and 3, let's take away 7 from both sides, they would go along with it. They'd say, okay, that's the rule. Math doesn't make sense. I'm used to it not making sense. And whatever you tell me to do, I will do. Well, here, if I try and tell them to do something that doesn't make sense, they will tell me that I can't do that. And that's how powerful this is. So, doing that, I could say, so I could have just taken 3 at one time. Yes, I could have taken 3. And how do I represent that? Taking away 3, taking away 3. Okay, the second thing I can do is, we can look at order, because, technically you could do this in many, many different ways. You could take one candy bar away, one candy bar away, and take -1, -1. You could say, well, I think I'll take a penny away, I'll take a penny away. And you could do -1 and -1, and you still are doing everything mathematically correct. You could say, maybe I'll take 2 away and 2 away. Okay, take 2 away, take 2 away. Everything's still mathematically correct. And then I'm going to go back to the candy bars, okay? But can you see that you're going to have a lot of written work here? And the idea is the students aren't going to want to spend a lot of time writing this out, okay? They want to get the problem and get it done with. So they're going to try and do as efficient as possible. Okay, so anyway, we take away 3 candy bars and 3 candy bars, and we're left with 1 candy bar, and 5 cents is equal to just plain 10 cents. And then what? Again, I could take 1, 1, 1, 1, 1, 1, or I could just say, well, I know I've got 5 I've got to take away from here. So I'm going to take 5 away from here. Okay, and the idea is, don't just tell the students, no, oh, take all 3 away, take all 5 away. Give them a good reason. Let them think about it. Discuss it. Discuss their different methods of solution. And the idea that, I want to do this as fast as possible. What should I do? And they're going to come up with these ideas. Okay, and it's going to make sense, and they're going to want to do these ideas. Overall, what's happening is we're going from concrete to abstract, and they're telling us the rules. We are imitating what they're doing here. Me as teacher, I'm just facilitating. I'm giving them a problem. I'm letting them solve it however they want, and I'm helping them to represent it in math terms, now in abstract terms. Okay, so there we have variables on both sides of the equations. We can also be talking about like terms. Like, for example, I could have 3 cents and a candy bar over here. And I could say, okay, on the right side, put 2 candy bars and a penny. Okay. And then I could say, oh, you know what? Add another 6 cents to the, well, let me start with a different problem here. How about 1 dime, 1 nickel, and 1 candy bar in the left box? Okay, and then we're going to put 5 pennies and 2 candy bars in the right box. Okay, and the value of the boxes are the same. What's the cost of a candy bar? Instinctively, they're going to take this 10 and this 5, because I told them 1 dime and 1 nickel. That's 1 10 and 1 5, and they're just going to combine them. They're going to say, well, that's 15 cents. They've just combined like terms. I didn't tell them 15 cents. I never said the word 15. I said, and if you heard, I said 1 dime or 1 10 cent and 1 5 cent and a candy bar. And over here was 5 plus 2c, or 2c plus 5. And if I would ask them, how do I write this mathematically? They're not going to write it like this. They're going to write 15 plus 1c, or 1c plus 15. They have combined like terms in such a meaningful way, they don't even recognize that they skipped that step. That they basically took a problem like this and they just said, well, it's going to be 1c and 15 equals 2c plus 5. Okay, so that's where we can talk about, well, geez, how did you know to do that? Okay, I said, well, these are the same things. Money is the money. I said, well, how come you didn't combine that with the candy bar? And they say, that doesn't make sense. Again, instead of the teacher saying, you only combine like terms, okay, the students are going to tell me why you have to only combine like terms. Okay, and me saying, well, that looks like 16. Look, 10 and 5 and 1, that's 16. How come I don't have 16c? And it just doesn't make sense when the students understand the situation in a concrete setting. Okay, but the important point here is that you can start talking about like terms. So I could start saying, okay, so we have one candy bar and a nickel over in this box, and then we add another dime to it. So one candy bar and a nickel. And we add a dime to it. And in the right box, we have 2 pennies and a candy bar and 3 pennies and a candy bar. So we'll say 1c and 2 plus 1c and 3. And I didn't put these up on top of one each other. I would put these on the right. I just ran out of room here. Instinctively, they'll say, well, that candy bar and that candy bar, they will probably not write it this way. They will probably just write it like this, and they'll add like terms. And again, you can start talking about that. You can say, well, why not this 1c and that 2? And it just doesn't make sense. Okay? So the idea of adding like terms, they can tell you. The only thing you're going to tell them is that it's called like terms, combining like terms. Okay, so now we've done variables on one side of the equation, variables on both sides of the equations. And always, though, we've always had just one more variable than the other. If you notice all these problems, one side had one more variable than the other, one more unknown. Now we're going to find out where you have more than one unknown on one side, where there's more than one. So let's say we have 16 cents. And 1 candy bar here. And over here we have 3 candy bars. Okay, so we can, of course, represent that abstractly. And say, well, how do I solve that? How do I know what's the cost of a candy bar? Okay, so in this case, it's easy to do this and take that out of the equation and say, okay, I could represent that down here, and then they start looking at this and say, well, what's the cost of a candy bar? It's like, well, I got to divide this into 2 equal groups. Okay, so let me just make this a little bit easier. So make them all into pennies. I'll make the dime into 2 nickels. And now I can say, okay, well, okay, so let's look at all the steps that they just did. The first thing they did when they had this all together was they decided they were going to take one of those away. How do I represent that here? Take away 1 candy bar from both sides. And I'm left with 16 equals 2 candy bars. And then I decided to break this into 2 equal groups. Why 2? Because that's what I see here. What would have told me that here? To break into 2 equal groups? The coefficient. Okay? So what they do here, I do here. They divide that by 2, they divide that by 2, and they find. And again, when they divide it into 2 groups, they ignore, take it out of the equation, they ignore the 1/2 of the group. Okay? And that's where I come up with this right here. Okay? So we could do several problems like that. You see, we have 2-step problems. We have to, first off, in this case, we isolate the variable, okay, by one step, just working with the variables and getting rid of the various amounts. That's what we call isolate the variable, but here they understand it in a way. We just have to give it that term. And then the second thing is, well, I think I took way too many. Then the second thing is, once we isolate the variable, only have variables on one side, then we divide by that coefficient is in essence what we're doing. And so if we do several of these problems, do them down here. So in this case we had 1c plus 16 or c plus 16. You can talk about that too. I'm not going to talk too much about that. And we if we do, several of these problems, like let's say we have another problem where we have 4 candy bars and 8 cents, and we let them 2 candy bars and 32 cents. Unfortunately, I'm running out of time. That's a 32. So if they had 4 candy bars and 2 candy bars, they're going to take away 2 candy bars from here. Left them with 2 candy bars and 8 cents equals 32 cents. And then they'll take 8 cents away from both sides. And 2 candy bars they'll have in the left box, and 24 cents in the right box, and then they'll break it into 2 groups. Okay, so I could do a problem, do another problem. Again, they do it here, we write it, we do it here, we write it, maybe do a third one, and then say, what do you notice in all these problems? When I have a problem like this where I have a variable on both sides and numbers on both sides, or just a variable on both sides, what's the first thing I'm always trying to do? And as they look at this, they're saying, well, you're always dealing with the variables first, okay? And I'm trying to get the variable all by itself on one side. That's isolate the variable, okay? So they can see through a pattern. They can mathematically reason what's going on here, okay? And then what do we do? Oh, well, then we decide we're going to break it into 2 parts or 3 parts. And how do I determine how many parts to break it into? It's the value of the number in front of the variable, they'll say. And I'll use mathematical language. I'll say that's called a coefficient. So you're saying I look at what's in front. Okay, so once they do that, once they come up with this pattern, what do I always do? I always give them a problem for the first time and ask them to do it abstractly. That's always the goal. Once they figure out, they start to see a pattern, then I have them try and do it abstractly. Okay? And what will guide them when they do this abstractly is what they did with the concrete items. And as they're looking at this, they're saying, oh, that's like 5 candy bars and 1 candy bar. That's right. I remember our pattern. We have to get rid of a candy bar. So we have 4 candy bars and 12 cents is the same as 32 cents. So I know I got 12 cents on the left, 32 cents on the right. I got to get rid of those 12. And I got 4 and 20, I got to break it into 4 groups or 4 parts. And then once they do it abstractly, I'd say, can you go ahead and check that concretely, because I want them to figure out if they made a mistake or not. And some of them will make a mistake. Okay? So then we do it again a few more times where I begin with the abstract, let them check with the concrete. And what I'm doing here is I'm letting them figure out how to do this, and I'm empowering them to figure out how to correct their own mistakes. Okay? And through this whole thing, the students are driving these rules. They have come up with these rules. They have come up with the patterns. Okay, now let's look at adding polynomials. A polynomial being something like 3x plus 4. There's one polynomial. And adding it to 5x plus 12. Okay, so that's a polynomial, that's a polynomial. So how do I add polynomials? Well, again, it always makes sense in the concrete. And whatever we do in the concrete, we translate to the abstract, and then the abstract rules, the rules come through. Okay? So maybe we have a situation where, I put this into an elaborate word problem. I say, Shannon's at an ice cream shop. She's sitting at a table. She has 5 candy bars. So this is what Shannon has. She's sitting at this table, she has 5 candy bars, and they all cost the same amount. They're the same type of candy bar, and she has 3 cents. So that's Shannon's. Her boyfriend Ted sees her and joins her. Ted has 2 candy bars, the same types as Shannon. Okay, they decide to combine their candy bars and placing all on the table. So Shannon places hers, Ted places hers, and they combine them. Okay. Seated at another table next to them is Mandy and Larry. Mandy has 3 candy bars. And they're the same type as Shannon and Ted's. And she has 14 cents. Okay, so that's Mandy's. Her friend Larry has 1 candy bar, the same as the others, and 13 cents. Okay, that's Mandy and Larry, and so they're sitting there, they look at them, they say, oh, look, they combined theirs, let's combine ours. And they combine theirs, okay? Well, at this time, the owner of the ice cream shop comes over and notices this is laying on the one couple's table, and this is laying on the other couple's table, and of course, it's very bright, mathematical type of owner, and he says, geez, the value that you two have, this amount is exactly the same as that amount. You know, if I know the value of each of these candy bars, and this costs exactly the same as that value and that value are the same. If you can figure out the cost of one of these candy bars, I'll give you a free ice cream cone. That's what he tells them. Okay, so naturally they're going to do that, to try and do that, and that's my challenge to the students. What is the cost of one of those candy bars? Okay, well, they naturally add these are polynomials, and we're going to see this in a second. They naturally combine the candies together and the monies together, the like terms, and they go through the exact same type of situation from this point forward as what we just did. Okay, the only thing new here is that they combined these two distinct groups here together and these 2 distinct groups here together. They added polynomials first. Okay, everything else is the same as what we just talked about. So let's see, 4 here, so I can take those away. I see 3 cents here and 3 cents here, and take that away. So I'm left with 3 here and this here. So I want to break this into 3 groups. This is 24, so I can just mentally do that and say each one of these is going to be worth 8. Okay, so let's go back to the beginning, because it's important that, again, they understand the situation, and that's terrific, but let's go right back to the beginning. Shannon was there, and she had 5 candy bars and 3 cents. And along came her boyfriend Ted, who had 2 candy bars, and I think that was it. That's all he had was 2 candy bars. Okay, and they're sitting there. They decide they combine them. How do I write combining? They do this. Okay, so when they combined them, what did they have? Well, they just naturally brought the like terms together. They said, well, okay, well, this and this go together. Okay, and I could play devil's advocate. I could say, what about the 3? How come I can't, because you have 7c plus 3, can I have 10c? And the answer is no. And they'll tell me, whereas in a traditional classroom, I could get away with that. Okay, and then on the right-hand side, over here, Mandy and Larry, let's see, she had, 3 candy bars and 14 cents. No, she didn't have 14 cents. 1 candy bar and 13 cents. So 3 candy bars and 14 plus C plus 13. Okay, and they naturally see that the 3C and the 1C okay. All right, so these are polynomials. And they combine polynomials by combining like terms. They combine those polynomials, they combine like terms. I mean, if I wanted to, I could have written them like this. I could say that's the one person's, that's the other person's, that's one person, that's the other person. Okay, and the idea is I can combine those to get this, and then I'm solving it the same way. Again, just following along with what they did there. All right, so that's how we can introduce adding polynomials. Okay, now let's look at this in terms of fractions. So what I'm going to use, though, I don't want to really cut candy in half. So what I'm going to do is I'm going to use paper for this, because I mean it gets kind of dirty, you know, if you're with money and candy, and you know I just don't want the students to be eating it later. So let's just say something like this. Let's just use this as the whole candy bar. So Hershey's candy, and that's one whole candy bar. And I'd say, okay, so let's say somebody has half a candy bar. Okay, so I'm just going to say half a candy bar. There's my half. Half a candy bar costs 7 cents. Okay. By the way, how would I write that? Okay. Before we had 3C, like for 3 candy bars, or 1C for 1 candy bar. How would I write that? I'm going to ask the students. Okay. And it's not going to be too hard for them to see this. Okay. And I'd say, okay, if half the candy bar costs 7, what does the whole candy bar cost? Okay. And the idea is, well, I could add half a candy bar here and 7 cents here. Okay, that does work. And so the whole candy bar costs 14 cents. Okay, that's very good. Concrete to abstract, so this is what you're doing. And believe it or not, this works. Even though this looks very strange to most adults, that's mathematically correct. Okay, and you get a candy bar equals 14 cents. Okay, I would challenge the students, though, to think about this as doubling this. I had half and I doubled it. So I doubled this and I doubled this. When I double, what does that mean mathematically when I double? Okay, multiply by 2. Okay, so I could have solved the same problem, and this is what we're used to seeing as adults, by multiplying both sides by 2. Two times 1/2, or 2 over 1 times 1/2. Okay, so that's 2 ways I could have done that. Okay, and I want to think about it in terms of multiplication, although they could do this. All right, so let's say we have, so again, this is 1 candy bar, this is 1/4 of a candy bar. So let's say I have 1/4 of a candy bar, and that costs 10 cents. So we're just going to use a dime. Okay, how do I represent that mathematically? So what's the whole candy bar cost? Again, they could add 1/4 and 10, 1/4 and 10, 1/4 and 10. And I could say plus 1/4 plus 10, plus 1/4 plus 10, plus 1/4 plus 10. And add them up till I get the full candy bar. Okay, I could do that. And I would do that. If that's what the students are doing, I would write that on the board. Okay, so again, I would just write plus 1/4 C plus 10, and just keep adding until I got a whole candy bar. Okay, the second way we could do it is, can I use multiplication like I did up here? And I have this on the board for us to look at. The idea is, yeah, if I make this 4 times bigger, and I make that 4 times bigger, I'll get the whole thing. Okay, so again, I can look at that. And the candy bar goes 40 cents. Like I say, which one was faster, which one's easier? A lot of them will want to still do this because this just makes a little bit more sense, especially with fractions. Okay, but we're introducing this and we're seeing that we're getting the same answer. Now, if they're a little bit stubborn about it, okay, and they might be because this might be their favorite way, well, I could really break it down to, we have a candy bar, and I do 1/12. And I say, well, 1/12 is worth, we'll just say 18 cents. What's a whole candy bar worth? Now it's getting to be a kind of tedious to keep adding 1/12 plus 18, 1/12 plus 1/12. In other words, beginning with a problem, and then doing this 11 times. Oops. doing it, getting 2/12, and then doing it again and doing it again, do it again. It gets kind of tedious. Or get to the answer real quick that way. So see, again, I'm giving them a reason. I'm not saying don't do it that way. I'm not saying don't do it this way, but I'm giving them a reason for wanting to do this, because I could even make this 1/100th, and it's going to be a real pain to do. Okay? So anyway, I'm writing my information on the board, my methods of solution, and whatever 18 times 12 is, I'll write that on the board. I've got this one written on the board. I had the 1/2 one written on the board. I could say, geez, what do you notice we're doing all the time? And again, there they are. They're exploring. They're finding patterns. In Bloom's taxonomy, they're creating a method of solution. And they find that pattern. And here it looks like I'm always multiplying by the denominator. Now, in all these problems I just did, the numerator was always 1. All these were unit fractions, and that's the way I'm going to introduce it, what are called unit fractions. That's what all these are, with a 1 in the denominator. Okay, and that's how I'm introducing it. I'm not going to have something else in there, because that's another step in the problem. So now we've got them able to do this and at least understand it, and then I would give them, of course, give them a problem and let them check it. Like if I said 1/6 of a candy bar is equal to 4 cents, what's the whole candy bar worth? And again, they could go plus 1/6, plus 1/6, plus 1/6c, plus 4, plus 4, plus 4, or they could do this. They came up with this pattern. They're going to check it out, see if it works, and then they can go back to the manipulatives and see if it works, and it does work. Okay? So again, I'm facilitating this instruction. Now, if we get away from unit fractions and go to the non-unit fractions, something where there's something in the numerator beside 1, and we can use candy bars. We could use 5/12, for example. So we could have, and I need a few more 12ths here. Okay, so there's 5/12 is equal to 25 cents. Okay, and I'd say, well, what's the whole candy bar worth? All right, it's going to be this is going to be difficult. 5/12 is worth 25. We know how to write that, of course. Okay, so what is that worth? Well, the idea is, and again, they should be the ones solving this. It may take several minutes, maybe 10 minutes for them to kind of figure out. I might go ahead and if they are having difficulty, say, why don't you make that into 25 individual pennies, which I don't happen to have here. But you make 25 individual pennies. Maybe I do have it here. Maybe I'll do this in the semi-concrete. I'll just have each of those. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4. There's my 25 pennies. And say, does that help me? The idea is that if you match up 5 pennies with each one of these, oops, 1, 2, 3, 4, 5, 1, 2, 3, 4, oh, we got too many in there. All right, so what I do with the 25, in step 1, I'm breaking it, I'm dividing that by 5. Why 5? Because I have 5 little units. Where would that be? That would be up here. Okay, so I break it into 5, I line them up, and then I can say that means 1/12, one of these is worth 5. So 12 of these would be worth 12 times 5, or 60. All right? I'd let the students do 2 or 3 of these, not really do too much with the equation yet. Just do 2 or 3 of these, because just breaking it up this way, just doing what I did here, is an extra step, might take a little bit of thinking. Okay? Now, when we finally come to a point, maybe they've done 2 or 3 of these, they understand what they're doing and why it makes sense, then maybe let's pretend like this happened to be the 4th one. So on the fourth one here, they go and they solve it, and I say, okay, let's go back to the original equation. What's the first thing you did? And they'd say, okay, I divided that by 5. I'd say, well, how would you know that over here? And it's like, okay, because I had 5 of these pieces. So I divided that by 5. All right, so if I divide that by 5, I can think of it like that. Now, this isn't going to look too good here. So how about if I say, when I divide by 5, is that the same thing as saying 1/5? And of course, that is the same thing. If I take 1/5 of this and 1/5 of this, okay, by doing that, when I multiply this, I could multiply it out, or I could just simplify it like that. Okay, that means I had 1 candy bar was equal to 5 cents. And now we're back to the situation that we had when we had the unit fractions. Okay, and then when I did that, I knew that, okay, 1 of these is worth that. I want 12 of those, a whole candy bar. Okay, and then that's where I come up with the candy bar is equal to 60 cents. All right, and I'd put that on the board because I'm going to start to notice, I want the students to start to notice a pattern. So, I mean, I could use base 10 blocks if this were a whole candy bar, for example, or a whole. And that would be 3/10 right there. Okay, so I don't have to just continue to use candy. I can start using some of these other manipulatives. So if I say 3/10 of a candy bar is worth 6 cents, what is this worth, the whole? Okay, so that's the question. All right, so if that's worth 6 cents, that means this, this, and this. Each one of these individually is worth 2 cents. So if one of these is worth 2 cents, I need 10 of those, so 10 of those would be worth 20 cents. We'll go from the concrete to the abstract. We began with 3/10. I'll just call these x, and we'll call them c, is equal to 6. And what I did is I looked at 1/3 of them. Or divided it in 3 ways. Okay, and then that gave me one of these is equal to 2 cents. And once I had that, there's our answer. Okay, now I have this on the board, I have this on the board, maybe a third one on the board. We could start, I could ask the students, do you see a pattern here? Do you notice something? Because I could say to the students, now I want you to solve a problem, you know, like, no, we'll just say, you know, so, and I want to solve this abstractly. You know, I don't want to use 8 of these because these would be 8/10 if I had 8 of these. And so the idea is, well, it looks like we always divide by the numerator. And think about that. Well, what does that mean in here? Oh, well, we're just breaking them down to find what one of these things is worth. Because when I want to find one of them's worth, then I can just multiply this by however many of these make the whole. Okay, so go ahead and try it. So it looks like you're doing this as 1/8. Okay, and you find out that 1/10 of these is equal to 2 cents. And then what do? Then you multiply that by 10 and that by 10. Okay, and then they could check it with the concrete items. So that's the way we get them to begin to look at fractions in terms of solving fractions and how they can build the method of solution for solving fractions and variables. All right, and at some point when they get good at this, if you want, you can show them the reciprocal. You could say, you know, let's look at this problem here and this problem here. And this would again be at a later date, maybe the next day's lesson or a day after that, and say, is multiplying this by 1/5 and multiplying this by 12, would that be the same as beginning up here and multiplying that by 12/5? Yes or no, and why? Or here, it would be the same as multiplying this by 10/3. Or here, multiplying this by 10/8. Okay? Again, it's always about discussion. It's about mathematical reasoning and the students seeing that, well, I guess it is the same, because when you look at this here, multiplying by 1/5 and multiplying by 12, do I get the same result by multiplying 12/5? And they can try it out. If that's important, to multiply by the reciprocal. And then how would you know to multiply by 12/5? You know, if you began with a problem like this or a problem like this. How would you know to multiply by 10/8? And of course they can see, well, it's just the reciprocal. They may not say a reciprocal. They might say, well, it's just the opposite, or you just switch those, you know, using non-mathematical terms. And of course we would just say, yeah, that's called the reciprocal. Okay, so basically what we're doing here, a very complex process, but it makes a lot of sense to the students. The students can figure out these very complex things, or at least they seem very complex. Really, they are not very complex. When we look at them in this way, if we begin with the concrete, give the students enough time to figure out what's going on in the concrete, begin representing it with the abstract, and then whatever they do here, mimic it down here. You can even play devil's advocate on the way, trying to do things that they will tell you is impossible, which means they really understand the concept first. Okay, so they go from concrete to abstract, they understand the concept. We put several problems on the board. We have them explore, analyze the problems, see if they find a pattern. Bloom's taxonomy. The pattern is something that they created, highest levels. And then we apply that pattern, or we evaluate it really at Bloom's level. It's more than applying it, it's evaluating it. Let's evaluate it with a brand new problem, except we're going to do it completely in the abstract, and then check it in the concrete to see if the patterns we found up here really do work. Okay, and that's the way we meaningfully teach variables from from beginning in 4th grade and 5th grade all the way here into 7th grade and even into 8th grade.